Hey there, 205. This is our last video on regression analysis, and it's just serving as like an extras video, just other things that you need to know about regression. So here we go. First of all, remember that most dependent variables are not feeling thermometers. We have been using feeling thermometers because it's sort of this intuitive measure that goes from 0 to 100. It's not that hard to conceptualize, but most EVs are not feeling thermometers. So for example, here I have a dependent variable that is 0 to 7, and each point on that scale represents how many days people talk about politics a week. So people that choose 0 talk about politics 0 days a week. People that choose 1 day a week. 2 all the way up until 7. That's our dependent variable. And our independent variable is the political knowledge scale that goes from 0 to 3. So now we have a dependent variable, and the unit is not degrees like a feeling thermometer. The unit is days. So you need to interpret that accordingly. So the way that we would do this is our coefficient for political knowledge is 0.249. So we would say for every point people move up the political knowledge scale, the number of days a week they talk about politics increases by 0.249 days. We just need to make sure that we have the units correct. So that's the first thing that I wanted to talk about. The second thing I wanted to talk about is comparing effect sizes. We talked about how we look for the direction of the effect, whether it's positive or negative, the magnitude of the effect or the size of the effect. That's what the coefficient is representing, and then whether or not it's significant. So I have run a regression here using our old friend, the Trump feeling thermometer, and I have a bunch of variables in here. So the question is, which variable in this model has the biggest impact or the largest effect size? Which one of these listed down here has the most or the biggest effect on how much people like or dislike Donald Trump? Now, the intuition is, well, I just look at the column for the coefficients, and whatever number is the biggest, that's the one that has the biggest effect. Technically, that could be true, but we actually can't do that. Why not? We can't do that because all of these variables are scaled differently. So, for example, the effect size of someone's race, which I have called white in this regression, that's captured completely because it's a dummy variable. We said the way you interpret this is white people like Donald Trump 5.48 degrees more than non-white people. Because it's only a 0 or a 1, and that's the interpretation, the entire effect size of someone's racial category there is 5.4. You know it all. However, the effect size for someone's age is not completely captured in the age coefficient. So it says 0.0731 for age. But we know that 0.0731 just means if you go up 1 year on the age variable. So you're only seeing a fraction of that variable's effect, but you're seeing the whole effect of the race variable. So if that sounded a little bit confusing, I have a visual to make this clear. We said for age, we interpret it as for every unit increase, so for every year someone gets older, the thermometer goes up 0.073 degrees. But we have to keep on doing that over and over and over until we reach the end of the scale. There are all these different points for age on the scale. But for someone's race, there's only 2 options. So going from a 0 to a 1, going from non-white to white on the race scale, that's the whole variable. So what if we were to add up all of these numbers on the top for age so we can see the full effect of age? If we were to add everything up, it comes to about 6.7. That's the full effect size. But the full effect size for someone's race down here is 5.48. That's actually smaller than the effect of age. You can see the comparison right here. You have to actually look at how it's scaled and then add everything up. So if two variables are scaled the same way, if they're both dummy variables, or if they're both 7-point variables, yeah, you can compare the effect sizes, but otherwise you have to actually add up that effect size. But doing that is obviously a little bit tedious. So we do something called standardizing our variables. And there's many ways to do this, but the most common way is to rescale all your variables to range from 0 to 1. If they're not already dummy variables that are just 0 or 1. So for example, if you have a variable that has 3 points, 1, 2, or 3, you can change that variable so that it's 0, 0.5, and 1. Now it goes from 0 to 1. There are fractions in between. You haven't actually messed up that data. All that matters is that the numbers are spaced the same way from one another when you transform it or rescale it. It doesn't actually matter what the numbers are as long as the spacing between them is maintained. If you have everything on a 0 to 1 scale, then you can actually compare the effect sizes to see which is bigger, which is smaller, and the bigger ones are the ones that have the biggest effect. I will show you what that looks like in just a second. So that's the second thing I wanted to say. Okay, what does it look like to see a regression in a published article? So we've been looking at Stata output for the last few videos, and it's been looking like this. This is not what a regression looks like in a published journal article. There's a lot of stuff going on this screen that we simply do not need to report in a published manuscript. So I'm going to show you what it does look like for when you guys come across something that's published. Okay, this is a study that I ran in graduate school. I was trying to see if people thought Sarah Palin's readiness to be president affected their impression of John McCain's sense of judgment, okay? So the dependent variable is John McCain's judgment. The independent variable is whether or not people think Sarah Palin is ready to be president. So first of all, you'll notice that all of the coefficients, which are the first numbers in this column, all those variables have been scaled from 0 to 1. So the coefficients are all between a very limited numbers here. So you can actually look at those coefficients and say 0.43, that's actually the largest coefficient in here besides the constant, which we don't really care about. So that's actually the variable that has the biggest impact on people's impression of John McCain's judgment. But you'll also notice that there's a lot of stuff missing. So over here in this sort of column, these are our coefficients. In the parentheses next to each coefficient, you have the standard error. We did not talk about that. We don't have time to talk about that. The standard errors are very important, and they will indicate whether you have a high or low p-value and find significance. But how do we know if something is significant? There's no column here for p-values. So what do? In a published article, you will see little asterisks next to each coefficient and its standard error. And the asterisks correspond to a note that is below the regression table. So for example, if a variable has 1 asterisk next to it, that means it is significant at the 0.05 alpha level. If it has 2 asterisks, that means it's significant at the 0.01 alpha level, and so on and so forth. Once in a while, those asterisk codes change, but this is a pretty typical coding scheme for significance. So that's how you would see it in a regular journal article. Everything's been cleaned up quite a bit. And then finally, what if my dependent variable is not continuous? Because we've been talking about how linear OLS regression requires a continuous dependent variable that has many, many, many possible values. So what if your research question was what causes countries to have civil wars? And your dependent variable is either the country had a civil war, it gets a 1, or the country did not have a civil war, it gets a 0. Maybe you're interested in whether the level of financial inequality in that country is causing countries to have civil wars. So your dependent variable, unlike a feeling thermometer, it can't go up and down more than 1 unit. There's only 2 options. It's 0 or 1. So it would make no sense to say something like, for every increase in financial inequality, our independent variable, civil war goes up, X amount. It can't go up more than 1 unit. You either have a civil war or you don't. So you cannot use a regular OLS or linear regression. You have to use something else. In fact, there are different types of regressions for different types of non-continuous dependent variables. It's beyond the scope of the class, but I wanted to let you guys know. So if your dependent variable is 1 or a 0, voted or didn't vote, the county has a female representative or a male representative. If it's 1 or 0, you use something called a logistic regression. It's more complicated of an interpretation, but we're not going to talk about that. If your dependent variable is ordered and has less than 7 values, so for example, if you get someone's opinion on a political issue and there's a 3-point scale or a 5-point scale or whatever, it's below 7, you have to use something called an ordered logistic regression. If your dependent variable is categorical, so if you're asking people, what party do you belong to? And it's Democrat, Republican, Green, Libertarian, if it's a category. Or you're categorizing countries. Countries either have a democracy, an autocracy, a monarchy, etc. These are categories. Then you have to use something called an unordered or a multinomial logistic regression. All of these different, we call them estimators, all of these different estimators have increasingly complicated styles of interpretation that you would learn in grad school. But I wanted to let you guys know because regular linear regression that we've been doing has limits to it and certain requirements that you have to meet in order to use that type of statistical test. So that's all I wanted to talk about for this video.